This case is example 10.1 of the textbook is to design a parabolic can follower displacement to provide a dwell with zero lift for the first 120 degrees of the motion circle, and to dwell at 0.8 inch in the lift for the can angles from 118 degrees to 210 degrees. It means that we have the rise interval. The can rotates from 120 degrees to 118 degrees. And the return interval, the can rotates from 210 degrees to 316 degrees. The problem is to calculate the displacements for the rise and the return intervals at the 10 degree of angle increments. We calculate the displacement of the rise interval first. We know each interval needs to use two parabolics to fit it. For the first part of the rise between theta 120 degrees and theta 115 degrees, the equation applies if we use phi is theta, subtract the beginning angle of 120 degrees. The amount of the rise error equals 0.8 inches, and the can rotation angle required, beta is 16 degrees. Then, the resulting expression is listed in equation 10.7. For the second part of the rise between theta 115 degrees and theta 180 degrees, the resulting expression is in equation 10.8. We can use equation 10.7 and 10.8 to calculate the displacement points on the rise interval, and the results are given in table 10.1. Can and follower systems need high accuracy for applications. For this reason, we normally work with at least 4 decimal places when doing can calculations. We know only CNC milling and precision grinding can achieve the accuracy of the cans. Let us move to the return interval. The amount of the rise error equals 0.8 inch too, and the can rotation angle required beta changed to 115 degrees. For the first part of the return between theta 210 degrees and theta 285 degrees, we also subtract theta for the beginning angle of 210 degrees to get phi, and then substitute all known values into equation 10.5. We can get the resulting expression for the first part of the return and list it in equation 10.9. For the second part of the return between theta 885 degrees and theta 316 degrees, again, we substitute all known values into equation 10.6. We can get the resulting expression and list it in equation 10.10. Finally, using equation 10.9 and 10.10, points on the return interval are given in the table 10.2. The resulting transition curves for the rise and return intervals are plotted in this diagram. Next video, I will show you how to calculate this displacement using Excel. Harmonic motion can be generated by an offset circular can with a radial follower, and is a common form to use for a displacement diagram. Cans with this type of transition curve is usually referred to as harmonic can. The entire rise or return is covered by only one equation in this case, so it's quite convenient to use it. The equation works for the rise of return interval. We will look only at the rise interval here. The equations for harmonic motion are found from the basic equation like this. We have three constants, C0, C1, and C2, need to be figured out. We also have three boundary conditions. At the can angle theta is 0 degrees, the displacement y equals 0, and at theta is beta, the displacement y equals L, and its first derivative equals 0. Then we get three equations to solve three constants. Substituting all the constants into the basic equation, we get the final equation like this. Using kinematics analysis, we have the displacement, velocity, acceleration, and jerk of harmonic motion. Its SVAZ diagrams are shown here. We can see the jerk is infinite at the beginning and end of the rise interval because the acceleration is discontinuous at each end point of the curve. This motion will generate vibration when the can rotates at high speed. Therefore, the application of harmonic motion is limited to moderate speeds. Example 10.2 of the textbook is to design a harmonic can to satisfy the same specifications as for example 10.1. The problem is to calculate the displacements for the rise and return intervals using harmonic motion. In this motion, only one curve is needed to fill each interval. The rise in the interval 120 degrees to 180 degrees can be computed using equation 10.11. Here, we subtract the can angle theta by the beginning angle 120 degrees, and the amount of the rise L equals 0.8 inches, and the can rotation angle required delta is 16 degrees. We can get the resulting expression for the rise interval in equation 10.13. Using this equation, the values for the displacement y are given in table 10.3. For the return in the interval 210 degrees to 316 degrees, equation 10.12 is applied. We subtract the can angle theta by the beginning angle 210 degrees. Here, the amount of the return L equals 0.8 inches, and the can rotation angle required delta changed to 115 degrees. Substituting all the values to equation 10.12, we can get the resulting expression for the return interval and list it in equation 10.14. Using this equation, we calculate the displacement y for the return interval, and this is result in table 10.4. About motions, for example, linear, parabolic, and harmonic motions have no zero values of acceleration at the beginning and the end of curves that cause infinite jerk. Therefore, They are limited to relative low speeds. The cycloidal motion have zero acceleration at the beginning and end of the curve, so it is useful for applications at relative high speeds. This diagram shows you how to generate a cycloidal curve using the graphical method. The formula of the cycloidal curve for a rise is given like this. So, we have derivatives from the first order to the third order. We can see a cycloidal transition produce a sinusoidal acceleration curve. Therefore, the accelerations at endpoints of the curve are zero, and the drags are finite. So, cycloidal motion has a good performance at high speeds. By the way, the textbook makes a mistake for the formula of the cycloidal curve in section 10.4.4. The cycloidal curve should be a sinusoidal function. Using kinematics analysis again, we have the displacement, velocity, acceleration, and the drag of cycloidal motion. SVAJ diagrams are shown here. We can see the acceleration is zero at the beginning and the end of the rise interval. So it is better choice than the harmonic curve because its drag is finite, where the cam follower with cycloidal motion can work for high speeds. Equation of the return intervals for four motions are given here for your reference. You see, uniform motion, harmonic motion, cycloidal motion, and parabolic motion. SVAJ diagrams of the parabolic motion for the rise and the return are shown in these two diagrams. We can see shifts of the displacement, velocity, acceleration, and the drag for the return are upside down with those of the rise.